Okay, so today in this video we come to one of the real gems of mathematics, which is Euler's relation. Okay, so just remember when we introduced the exponential function, so we had the exponential of a number x is given by 1 plus x squared over 2 plus x cubed over 3 times 2, which is 3 factorial, so I can write that as 3 factorial, plus x to the 4 over 4 factorial, etc. And I can write 2 as 2 factorial, and x as 1 factorial. Okay, so we get this infinite series of terms, and this converges to a number. So the denominators go very quickly to infinity, and we get something which actually comes out to a number. Now, you can show also that you have similar expressions for sine and cos. So you can show that sine x, where you always measure things in radians, so sine x is of the form x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. So all odd terms, you still have the same factorial at the top as the number at same factorial at the bottom as we have the number at the top, and the signs are alternating as we go along. Okay, and similarly, there's an expression for cos which begins 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, etc. So from these beginnings, we're going to get something very nice involving complex numbers. So what happens if we put I in here? Okay, so let's just have a look at this. So if we put e to the ix, what do we get? So we just have to substitute ix wherever we have x. So this is equal to 1 plus ix, so that's over 1 factorial if you like, plus, well, instead of x squared we get ix all squared, and I squared is minus 1. That's the whole point of I. So what we get here is minus x squared over 2 factorial. And then the next time we get x cubed, so we need to put ix cubed in there, so that's I cubed times x cubed, and I cubed is equal to I times I squared, so that's just the same as minus I times x cubed. So here we get minus I x cubed over 3 factorial. Then we get plus I times x all to the power 4. I to the power 4 is equal to 1 because it's I squared squared, so it's minus 1 squared. So that's just, so we get I to the 4 is equal to plus 1. So that's just plus x to the 4 over 4 factorial plus, so then we'll get x to the 5, ix all to the 5. So x to the 4 is equal to 1, so that just comes out at I x to the 5 over 5 factorial. And then if you carry on, you'll see that the next one is minus I x to the 6, sorry, minus x to the 6 over 6 factorial plus minus I x to the 7 over 7 factorial, and so on. Now what we can do is separate this into the real and imaginary parts. So you see that the imaginary parts are the alternate terms. So let's just pull out the real terms. So we get 1, we've done that one, minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. And then the imaginary terms, we can take out the factor of I, So we get I x over 1 factorial, so that's just x over 1 factorial, or just x if you prefer, minus x cubed over 3 factorial, plus x to the 5 over 5 factorial, and so on. So what we have is precisely the cos and I sine. Okay, so let's just rewrite that. Let's just so that's just cos and that's sine. So putting that all together, this is just cos x plus I times sine x. And this is Euler's relation. So it's sort of a very, very beautiful result, combining complex numbers, exponentials, and the trigonometric functions. Okay, so let's just have a look at a few results here. So let's just give you some examples. So e to the I times 0, that should be same as e to the 0, and anything to the 0 should be 1. So that's e to, so if we put 0 in here, so that's cos of 0 plus I sine of 0. Well, sine of 0 is 0, cos of 0 is 1, so that's equal to 1, what you'd expect. So and another one, e to the I pi. So e to the I pi is, so that's going to be cos of pi plus I sine of pi. Well, what's cos of pi? So cos starts off at 0, at 1 goes down to 0, and then at pi is minus 1, and sine starts off at 0, goes up to 1 at pi by 2, and then comes down to 0. So that's just equal to minus 1. So e to the I pi equals minus 1, which is a very beautiful formula, combines sort of some of the most beautiful simple constants in mathematics, the exponential constant e, I, the square root of minus 1, pi, the ratio of the radius to half the circumference, and minus 1. So that's a very beautiful formula. Okay, so what else can we do with this? Well, we can pull out some nice formulas for cos and sine from this as well. So Euler's relation was e to the I x equals cos x plus I times sine x. Now if we put minus ix in here, so that's like putting I times minus x, so that's just the same as putting minus x in, so that's cos of minus x plus I times sine of minus x. Now cos is an even function, so you know cos goes like that. So if we've got some number x, then cos of minus x is going to be the same thing. So cos of minus x is the same as cos of x. And similarly, or kind of the opposite rather, sine of minus x is minus sine of x, because sine is an odd function. So sine goes like that and so on. So if we're at minus x, then we're at the minus value of where we would be at plus x. So I can change sine of minus x into minus sine of x. Okay, so what happens if I add these two together? We get e to the ix plus e to the minus ix is equal to 2 cos of x, and those two cancel. So I can just divide both sides by 2 and get a nice formula for cos of x in terms of the exponential function. So it looks a lot like the hyperbolic cos, which is where the hyperbolic cos gets its name from, if you've done the hyperbolic cos yet. And so we get that nice little simple formula. So similarly, we can subtract. So we get e to the ix minus e to the minus ix. And this time the cos's will cancel. And we'll get I sine x minus minus, so that'll be plus, so that'll equal 2i sine x. And again, we can divide both sides by 2i, so we get that sine x is equal to e to the ix minus e to the minus ix all over 2i. So we get these very, very useful formulae here in terms of cos and sine, in terms of the exponential functions. Okay, so we'll look at some examples of those next time.